All right, chapter 3 will begin to talk about the derivative. It's a pretty long chapter. I've broken it into essentially two halves. You're going to see, I think, 5 or 6 sections in this unit, and then the next unit will contain a few more sections from chapter 3, as well as some chapter 4 stuff. Um, so, introduction to what a derivative is. The derivative is the slope of the tangent line to the curve, and you can evaluate it at a point or just make another function out of it. In order to determine what a tangent line is, we need to talk about what a secant line is. So these lines, this red line here, or orange or whatever, is a secant line. And when we're looking for the slope between those 2 points on the given graph. Now, if you notice, if instead of taking this a plus h here, if we took a different value, say, if we made our h here, we're going to get a different slope entirely. And we're looking for the slope. So effectively, if you connect 2 points of a function, the slope between them is the same method that you would solve for in general algebra. Y2 minus y1 over x2 minus x1. Or this guy right here. So the f of x is the y evaluated at the one value of x, and f of a is the function evaluated at the other value. All right, so we've got 2 different points. We've got some value and another some value. Okay. Well, ultimately what the tangent line is the limit of this secant line. So basically, as we get closer and closer and closer together, what do we get? So if you see down here, they're taking points closer and closer and closer to this A. So way out here, we've got one slope. This is going to be less of a slope. This is going to be less of a slope still, until eventually we're just either just touching the one point and nothing else, or if you're part of the line, it could all be the same thing. So first, let's talk about and solve a secant line. So I've got a couple problems from the suggested homework. We want to find the slope of the secant line. So we'll use that formula above. So we're looking for, m secant, m for slope, is equal to, the function we're going to use is the function we have highlighted there, or the formula. So f of x minus f of a over x minus a. So we're going to want f of 5, that's our outer point, minus f of 2 over 5 minus 2. Again, essentially the way you would calculate slope anyway. This one, f at 5, will be this guy here, and f of 2. Again, I'm just plugging in the numbers into my f of x function that I have. And 5 minus 2 is simply 3. So let's continue to evaluate this. We've got 27 in our first, minus 15 over 3. That equals 12 over 3, which equals 4. And this is not surprising at all. In fact, if you look at this equation up here, this is a line, right? And this is also in the form y equals mx plus b. Again, this is slope-intercept form. So here we have the slope equaling 4. So essentially the secant line is just going to be part of the actual line. It's going to be the same line, because we're making a straight line that's touching a straight line, and that's the only thing we can do since we've got 2 points. If we're only touching one of the points in the line, yeah, it can intersect it. But if you're touching 2 different points in the line, it's the whole line. All right, so problem number 7, however, we don't have a straight. So this one's going to look more like this, y equals root x, or f of x equals root x. It's going to look more like that. So I can't just pick 2 points and have it be the same exact slope as that all the time, because the slope is changing for this function. But let's give it a shot here. So I want m secant f at 16 minus f at 1. Now the book has given you some nice perfect squares there. So f at 16 is root 16. F at 1 is root 1, and that's 15. It's 4 minus 1 over 5, which is, 15, which is 3 over 15, which is 1 over 5. And that is the slope of the secant line for that function between those 2 points.